Hello, mathematicians! Today we're looking at the converse to the right triangle theorem. So this is kind of a new theorem that's going to play off of reversing a right triangle theorem. And it's really going to look at the question of what if the triangle ain't right? What if we don't have a right triangle? How can we prove that something is a right triangle? So let's go ahead and get started. So here's where we're starting. I'm going to show you what this actual proof says, what the converse means. We know the right triangle theorem. It tells us basically two related statements. I've been giving you a right triangle. Been saying, here's some sides, they're in a right triangle. So if you have a right triangle, we've been using this relationship of a squared plus b squared equals c squared, or the sum of the square of the legs equals the square of the hypotenuse. So it's really an if-then statement. I tell you it's a right triangle, you tell me that we can use this relationship. The converse of the right triangle theorem is just going to switch these around. It's now if you have the relationship, the sum of the squares of the legs equals the sum of the, if the sum of the squares of the legs equals the square of the hypotenuse, if you have a squared plus b squared equals c squared, then you can tell me that you have a right triangle. So notice that it just kind of switches these statements around. That means that I might not give you a right triangle. I'll give you the sides this time. You might know, okay, this side is this long, that side is this long, and this side is this length, but I'm not telling you that it's going to be right. So, why is this true? Let's look at what this actually means. So I have a little video myself, and I'm going to turn the video down low because I'm just muttering to myself, and we don't need to hear anything creepy like that. So notice I'm reaching out, I have this right triangle that forms here. But now notice what happens when I let that hypotenuse shrink in, it became smaller. And when I pull it out, it becomes bigger. So just because even though these side lengths aren't changing, the hypotenuse length, that longest side here, will actually either stretch out our angle or it'll shrink it in. Let's look at a quick little view of each of these together. So we start out with this right triangle right here. We saw, okay. And it's really that this hypotenuse has hit this sweet spot where that it can actually hold these two legs together in this perfect 90-degree angle. But the next thing that happened in the video is I let this hypotenuse shrink down. I let the rubber band pull the two sides together a little bit. So this one had this relationship, that sweet, perfect relationship. But when I let this guy pull in a little bit, so now my hypotenuse has shrunken just a bit. Notice that also means that it pulled the two legs together. So now I have something less than 90 degrees here. We call this an acute triangle in this case. And notice this means that you'll find a squared plus b squared is going to be greater than c squared because my hypotenuse length right here is too small. It won't make that equality. It will be a less than sort of equality here, or inequality here, because that hypotenuse has shrunk down and it's too small. Then what I did is I opened it back up. So now I'm letting that rubber band stretch as much as I can. I'm going to shift my own image. So when I let it stretch out beyond what that right angle is, notice again now it's pushing the sides of the two legs apart. So now it's going beyond 90 degrees here, and we call that obtuse. So now we have that hypotenuse is too long for that perfect relationship right here. So now let's go ahead and put into practice. So I'm going to go ahead and get us out of this. No, I don't want to keep any of these. And let's look at practice. So we're really questioning, does this exist? If it does, we're in a right angle or a right triangle. Yes means right triangle. No means that we either have an obtuse or an acute triangle. It cannot be right. A sloppy thing. So we're going to try probably 2 or 3 practice problems right here real fast. So notice now I'm giving you all the sides. The first question you might have is, well, which one's the hypotenuse here? You're not clearly telling me. No, I don't need to. The hypotenuse is always the longest side. The diagonal is always the longest. We know this. So choose the thing that's the longest. I know that 33, the square root of 33 is between, let's see, there's 25 is 5 squared, and there's 36, that's close. Too big, but that's 6 squared, so that means that 7 is actually going to be big, because 33 is between 5 and 6. So I'm going to go ahead and get started then, knowing that this is my hypotenuse right here. I'm going to see what happens when I do 4 squared, which is one of my legs, plus the square root of 33 squared. Notice those will cancel. It's another one of my legs. And does that actually end up equaling 7 squared, the length of my hypotenuse? I'll find 4 times 4 is 16. The square root of 33 times the square root of 33 just gives me back the plain old 33. Does that equal 7 squared or 49? And I find, hey, 16 plus 33 is indeed 49. So this triangle right here is a right triangle. So we're just kind of running this guy backwards, right? We're running the right triangle backwards. So I've just proved that I have a right triangle. Let's look at another example. This one's in blue, so I'm going to use a blue pen, as is only correct. Okay, so again, I have to find my hypotenuse, which one is actually the longest. Square root of 40, well, we already know that 36 is less than 40, and that's a perfect square. 49 is too big, so it's between 6 and 7. That's our smallest side. That is not our hypotenuse. That means that 13 is our hypotenuse right here. All right, so let's try to put it into our right triangle theorem. Let's see what the relationship is. One of my legs, square root of 30, squared, plus my other leg, squared. How does it interact with my hypotenuse, or 13 squared? Square root of 40 times square root of 40 is just 40. These guys cancel their inverse operations. 11 squared we memorized was 121, and 13 squared is 169. This gets me 161. That is not equal to 169. So I know that this is not a right triangle because it didn't work. So it's not a right triangle. If I wanted to go one step further, I could also say, I'm using a little shortcut as my picture for my right triangle, by the way. I could also say, hey, my hypotenuse was too big. So imagine again that we have that hypotenuse and it's pushing out because it's too big. So this guy is obtuse. Obtuse. Let's do one more example. I think we have time for one more. Let's see what happens here. I have lots of examples to pull from always, because you can always just make them up. See how they interact. Let's do this guy. We have 25, 27. The square root is 74. The square root is 74. Okay, here we go again. Square root of 74 has to be between the square root of 81. That's 9. And it has to be between 64, the square root of 64, that's 8. These are much bigger, so this guy's my hypotenuse. I need to switch to green, because that's the way it goes. Hypotenuse. Okay, so that means I have 25 squared plus the square root of 74 squared. Again, I'm just plugging in leg. How does it interact with hypotenuse? Let's find out. 25 squared is 625. It's a good number to memorize if you ever need to. Who knows? And 27 squared, oh, for 27 squared I actually need some side math. Let's find out what 27 times 27 is. Side math times 7 times 7 is 49, carrying the 4. 7 times 2 is 14. Oh wait, plus the 4. Look at this. I have to tell you, honestly, I didn't grow up using this math. I actually really preferred lattice multiplication. I always thought it was beautiful. I only used that one. So I had to relearn this as a teacher. I make mistakes. It's okay. I'll catch up. Hopefully. Or you'll catch them for me. 2 times 7 is 14. This time I carry the 1. 2 times 2 is 4 plus the 1. This time I won't let it go. It's 540. Add them together. 9, 12, 729. All right. Oh, what have I done? Let's put that down in our answer. All right, 625 plus 74. Ooh, I don't know if this is going to equal. It's not looking very likely. Oh no! 699 is much less than 729. So again, our hypotenuse is too big. This is not a right triangle. This is obtuse. Obtuse. Cool. I hope that helps you get started on looking at the converse. Another fun way to do it is take any 3 things that exist in your home. Try to see if you can make a right triangle out of them. Try to use pens. Try to use toothpicks. Try to use, I don't know, edges of paper, books, anything you want. That way you are actually implementing the converse of the right triangle theorem. All right, have a great time practicing this, and we will see you soon. Happy exploring.